Hello everyone. Welcome to the first lecture of our comprehensive course on RCC building design using ETABS and manual checks. So in this first lesson, I'll be starting from very basic because I want everyone to understand the basics first. If you are a already practicing engineer, or if you already know this concept, then that is very good. But those who are new, like those who are college students, it is very important for them to understand the fundamentals. So I will start from very basic in this first lecture. So when we are talking about RCC, you can see here this particular term RCC, reinforced concrete, cement concrete. Now in this, it is very clear that what we need first, we need concrete, right? We need concrete. I will just come to this reinforced part in a while. First of all, let us understand what concrete is. This is the actual material that is needed for RCC structures, right? Now like all of us know, if you have already studied about concrete in our curriculum, in our BTech or diploma curriculum, or whatever course you have done regarding in civil engineering, that concrete is nothing but the mixture of these things, the coarse aggregate. If you see here, the coarse aggregates, the cement, obviously this is the main ingredients, the fine aggregates, and water. Obviously there will be air and admixtures. Now why admixtures are needed? Admixtures are needed to increase the setting time of the concrete, or for many reasons. But the main ingredients of the concrete is our coarse aggregate, fine aggregate, cement, and water. Okay, and what we need to do, what we do actually in concrete technology, we have learned that we need to find out the ratio of mixing these things, right? We will learn about the ratios in detail in our later sessions, but today we will just know the basics. Like we have different grades of concrete, like we have M15 grade, M20 grade, M25 grade, M30 grade, and there are many higher grades like M40, M50, like that. And like in general constructions like G+1, G+2, G+4, we hardly use those higher grades, right? We used to go up to M30. So I will also talk about the other grades also. So these are the basic grades. We do not use nowadays this M15 grades, even the M20 grade also. Maybe we can use in case of if we have slabs, like without with less loading. Okay, but most of the cases we used to go with M25 and M30 grade. These are the very popular grades that is used in the on site, right? So now this is what we call concrete. If you see here, the mixture of all these things, right? So we understood what is concrete. We already studied this in our BTech curriculum, or in our civil engineering curriculum, right? Now how we mix these things, we have got these ratios from M15, M25, M30. Now how we mix this? Obviously we know that in smaller sites it is done manually using you can see this image, this first image. People are mixing the cement, the coarse aggregates. Now these coarse aggregates can be stone or can be brick chips, right? Like in our in layman language we used to call them brick chips, right? Like of 20 mm size. Okay, so it can be stone or brick, the coarse aggregate. Fine aggregate, obviously it is like sand. Cement, we know there are different brands of cement, so it's totally up to you what you want to use. And we have water. Obviously we need to find out at one amount we need to mix the water, and like that is what called water cement ratio. We need to find out the water ratio. Then we add admixtures to increase the setting time of the concrete, right? Now so this is the first way, manually mixing the concrete, the ingredients of the concrete. Then we have this mixture machine, the second case. Here also it is done manually, just all these things we used to put here in this particular compartment, and then we have a mixture inside which will rotate, or you can say which will mix these things by rotating, right? And in a bigger sites where we need like higher amount of concrete, right, in that case we used to use this trucks, mixture trucks, right? There the concrete we bring from the you can say there will be a different place where the concrete will be like they will be creating the mixture of the concrete, and they'll put here in this truck, and this it will bring the concrete mixture to your site. So it is used in case of very bigger sites, okay, large projects where you need a very higher amount of concrete. So in that case we use this mixture trucks. So this is very fundamental, like we learned about the concrete, the ingredients of concrete, and what we how we mix those ingredients on site. Okay, now let us understand the important thing, that when we see a concrete structure, so when we see a concrete structure, so this is the example of concrete structure, you can say this is the example of concrete structure. That means the RCC structure, I will just write RCC, it is not only concrete. So we see RCC structure like this, right? Now why we call these things RCC? If the only component is concrete, then why we use the term as RCC, reinforced cement concrete? Why we use this? Now let us understand this. I hope all of you know about this, but still let us just discuss the few basics, fundamentals. Suppose I have a beam here, you can see a simply supported beam, and we have a point load F on this beam. Okay, so what we have here, the beam is bending downwards. Okay, the beam is bending downwards. So what we understand from here, that when the beam is bending downwards, that this particular the bottom fibers will be in tension, right? And the top fibers will be in compression. Okay, the top fibers will be in compression. So if I just draw a beam section here, okay, let me just draw. Okay, how it will work. So if you just see, suppose this is the beam cross section, and I just want to draw the neutral axis, suppose here. Okay, so what I'm saying, like when we have the load from here, this load F, these top fibers are in compression, and the bottom fibers are in tension, right? So like what we know, that concrete is strong. Concrete, if I just write here, concrete is strong in compression and it is weak in tension, right? So if I just draw the strain diagram here, you can see strain diagram. We used to write it is compressive strain, it is tensile strain, right? Something like this. So it is pretty good to you can say the stresses that will be induced due to the compressive strain. The concrete is pretty good. Here you can see the diagram. So concrete is pretty good to tackle the compression. But if you see here, due to the tension in this bottom fibers, here you can see the cracks. Here you can see the cracks, right? Here you can easily see the cracks. So the concrete is not strong enough to tackle the tension. So that's why to tackle this tension, what we provide rebars or reinforcement bars, right? You can see the view here, 3D view, where we have the concrete beams and columns, and what we have done, we have provided these bars in the longitudinal direction. So how it will be suppose here provided here. So what we expect that the compression will be taken by the concrete. Just do this. So the compression will be taken by the concrete, and this tension part, this tension will be taken by the reinforcement provided. So this is the compression zone which will be tackled by the concrete itself, and here in the tension, obviously partially it will be tackled by the concrete also, but in most of the part or most of the tensile stresses will be taken by the reinforcement provided here. There are few things that we need to provide reinforcement at the top also, but that is a different thing, we will discuss later. But the fundamental is that we consider that the compression will be tackled by the concrete and the tension will be tackled by the reinforcement partially and the concrete partially, but most of the tensile stresses will be taken by the reinforcement, right? So when we are providing this reinforcement bars, then we are not seeing this kind of phenomena you can see here, right? So the compressive stresses due to you can say the strain is tackled by the concrete, and the tensile stresses are tackled by the reinforcement provided there. Okay, so it is same in case of column also. If I just draw a column, suppose in a 3D mode, like in isometric view, so obviously if I have a load like this, so there may be bending in the column like this. It is also possible. So this particular side will be under compression, this particular side will be under tension, right? So to tackle the tension, we need to provide the reinforcement. Now in column, we do not know from which side. Even there can be lateral loads also. I will just talk about the loads in a while. So there can be loads from this horizontal direction also. So we do not know from which direction we need to give reinforcement, or in which direction we will be having compression and tension. So that's why we used to create cages like this in case of columns, right? Even in case of beams also we used to create cages like this, but that is different concept. We will explain in our further lessons, in our next lessons. Okay, so the same case we understood that it is the same as in our columns also. So what is column, what is beam, we know, but I will explain again. So that's why, as concrete itself is not capable of taking all the forces coming in the member, as we are taking the help of reinforcement bars, right, steel bars, to tackle the tension in the coming in the concrete due to the load. That's why the structure made up of concrete and steel are called RCC, reinforced cement concrete. So we are using this we can say using these bars, steel bars, to reinforce the concrete, to provide reinforcement to the concrete, right? So you can see it has provided reinforcement here. It's like a stitch, right? So this is actually reinforcement, and that's why these bars, steel bars, are called reinforcement bars, right? So that's why the structure made up of these reinforcement bars provided embedded inside the concrete sections are called RCC structure, right? So this is pretty clear to, I hope it is pretty clear to all of you. Like this is very basic, we all know about it, so there is nothing very complicated. This is the fundamental of our civil engineering, right? So let us now know about the parts of a concrete structure. So here we have a very simple image that I have taken from Google. You can always find it if you search the parts of concrete structure. So I've just taken few images to explain from Google. Those none of these images are taken by me or created by me. It's just taken from the Google to explain the things. Okay. So now here let us understand the various parts of a concrete structure. So if you see here, this is at the very bottom. At the very bottom, I'll start from the bottom. So at the very bottom, we have this rectangular or square pads kind of thing, and here it is written pad foundation. It can be in different shape. Okay, foundations can be in different shape. These are called actually foundations. Why these are called foundations, I will explain in a while. So this can be in any shape. This can be combined for these two. This can be, you can say, a whole as a whole for all the columns like this. It is also possible in different situations when columns are closely spaced. But at the very bottom, what we construct for a RCC structure are called, let's go back here, yeah, are called the foundations. Okay, so at the very bottom of the structure, what we construct for RCC structure are called the foundations, and these foundations will be resting on the soil itself, right? These foundations will be resting on the soil itself. We used to see, you can see it is a given depth of foundation. So actually this is the ground level, and below the ground level we will do excavation and we will provide this foundation, right? After like completing the foundation construction, then we will come up to this ground level with these columns, and here we will be creating a beam connecting all the columns, right? It is the very you can say very common construction process. So here you can see these beams. These beams can be like in general practice, suppose from 0.6 meter to 0.9 meter or 900 mm. In mm I'm writing 900 mm to suppose 600 mm from the ground level. Suppose this is the ground level. Here we have provided the foundations, and we used to go up to here, and here we provide a beam like this. Sorry, let me just turn off this. A beam like this. So this is what I call 0.6 to 0.9. Okay, so this particular beam, why we provide, suppose like here we will be having soil filling. Now if you just create the beam at the ground level itself, during the rain there is a chance that the water will be going inside your house or inside your room, inside your home, right? Even there is a issue of like if you have water table very close to your foundation level, or even in case of rain, like there will be a chance of damp, you can say having dampness, right? So what we provide, you can say we provide a beam from where we will be starting the walls, and this beam is required even structurally because suppose you can see here the column will be going up to the next floor level. So this the next level where we will be having the floor slabs, this is called the floor level, right? So here we have one floor level, another floor level. So here this, as it is above the ground, so we used to consider it as plinth level, or you can say ground floor level, and this is suppose the first floor level, floor 1. Okay, and this floor to floor height in case of residential structures we consider maybe 3 meter, and in case of commercial structures it can be 3.6 to 4 meter or more than that. That depends. Now if I do not provide a beam in between, then what will happen? Suppose I'll be having columns like this, and it will go up to 3 meter. So if I do not provide a beam in between this, the column from the very top of the foundation, we need to consider the length. So the length will be very higher, maybe about 6 meter. In that case, we may have a condition called slenderness, which we will explain during the column design concept. Okay, we can have a condition called slenderness, which is not desirable. Okay, it is very simple. Let me just explain in a simple manner. Suppose you have a stick, bamboo stick, like this, and you have another bamboo stick like this. I'm just comparing the heights, and you provide load, you provide a pressure from the top, keeping the bottom at the ground. What will happen? If you see the deflected shape of the two sticks, the deflection in this stick will be very less, but in the deflection in this stick, if these are of same thickness, will be very higher, right? So that's why now if you provide, suppose you have asked someone to just grab this particular part, what will happen? You will see the deflection reduced to like this, similar to this one. Okay, so that's why we provide these connecting beams, which will be connected to all the columns like this, like a band, like this, to reduce this particular phenomenon. This is what slenderness is actually. Okay, we will learn about this in detail mathematically, but this is the fundamental idea of slenderness. So to reduce the slenderness in the column, we provide a beam in between. So this is also the need of this particular beam. Now, as remember, plinth beam, this beam is called plinth beam. This is the first beam that we create after the foundation. Okay, after the foundation, the first beam if we create in a structure, it is the plinth beam of the structure. So many of the structures may not have plinth beam, that is different. We will explain, we will get to know these things later on, but in general construction, small houses, even in the major projects also, you will find that plinth beam is the first beam that we construct in a particular building. Now there can be beams at this ground level also. Can be there is possibility to have a beam at this ground level also, which we call a grade beam or ground beam. So that is different. That is in specific cases we may provide, but as I said, in general construction, we will be having the plinth level. This particular beam we call plinth beam, and this level we call it actually plinth level, right? In this plinth level, we used to provide another thing which is called, you can say, damp proof course. Okay, we provide a layer of damp proof course. Why? Because suppose you have, this is my ground level, and you will be having rainwater here. Okay, so there should not be any dampness in the wall. Suppose you have the wall here, right? So the water should not, what we call in our language, it is like there should not be any seepage of water in this wall. Okay, so if we get, you can say in a very simple concept, suppose we have soil here, right? And we are pouring water in this particular areas. What will happen? Soil have these gaps, so we will be having water inside in these gaps. And suppose we have wall here. So what will happen? This soil will, this water will try to create dampness in this wall itself. So that's why what we provide damp proof course in this at the top of the plinth beam. Okay, so now if the height of the plinth beam is very high, suppose in some area, some places you may see that the height of the plinth level is 1 meter also. So in that case, maybe the damp proof courses are not required. Depends on the availability of water, or you can say on the accumulation of water, right? So that is the reason we provide damp proof course, but it is not common everywhere, right? So this is structurally, we say that this is the need of plinth beam to reduce the slenderness in the column. And then we create the floor, the first floor. We will be giving filling here here it will be soil, and then we will provide the wall. So it is the wall, right? So here you can see the foundation, then it is soil. Okay, here we may have filling of sand also, and then we have this plinth beam. At the top we may have damp proof course, and then we will be having the walls here, and this is the ground level. Okay, this is the ground level. So this level we call it as plinth level. Okay, so you can see it is a better view of plinth beams, how it is constructed. You may see this kind of beams now everywhere during the construction, right? And then we have the next beam below the first floor, and these beams are called our floor beams, right? Why it is said lower column? Because it will be below the floor beam, and most of the part of the column will be like the column which is below the plinth level will be inside the soil, right? And then we will be having these upper columns above the first floor level. Now if you see these floor beams at the first floor level, now there are some smaller beams also. Remember, the beams which are connected to column, like this beam, you can see it is connected from this column to this column, this column to this column, like this. So any beam which is connected to one support to another support, and it must be a column, then in case these beams are called as primary beam. You can see it is written here, these beams are called as primary beam. And the beams which are connected from beam to beam, like here you can see here these beams are connected from beam to beam, this beam to this beam, or any one end of the beam is connected to another beam, like this particular end of the beam. If I just talk about this beam, this one, so one particular end is connected to the column, the other end is connected to the primary beam. So these beams also we call it as secondary beam. You can see here. Okay, these are called as secondary beam. So the primary beams are beams which are connected to column, and the secondary beams are beams which are resting on others primary beams, or any end of the beam is resting on primary beam. Okay, if we have one end which is resting on the primary beam, then also we will be calling that beam as secondary beam. Okay, then above that we will continue the same thing. We will be having the upper columns, again we will be having the floor beams, we will be having another floor. Above this floor we will be constructing the floor slab. This is called the slab, right? RCC slab. Will be putting the reinforcement like this, and we will pour the concrete here, right? These are the slabs. So this is the fundamental you can say basic components of a RCC structure. So when we will be having load, now what is load? Like you will be like you may keep a chair here, you will be the people who will be occupying this building will be coming here. So these are the loads coming on this particular structure. Okay, so how it will be transferred? It will be coming to the slab. We will discuss it in a while. Let me just let us discuss it in next slide, not here. So so this is for now, this is the type of RCC components we have. One is column, then beam, then slab, and at the bottom we will be having the foundations. Okay, it can be in terms of pad foundation, that means the smaller pads, or maybe as a whole pad for all the columns, or maybe combined for 2 or 3. It is also possible. And there is another type of foundation called pile foundation. We will explain it later. Okay, now let me just show you few different kind of structures also in case of RCC. Now here in this particular kind of structures, here 1, 2, 3 images we have, you will see that we have slabs here, these are slabs, and we have columns, right? But we don't have any beam. We don't have any beam. right? So this particular system where we have columns and slabs, this particular system is called flat slab system. This particular system is called flat slab system in RCC. Okay, the load will be transferred directly from slab to the columns. The load will be transferred directly from slab to the columns. So there is no other way of transferring the load actually. And this kind of structures are not recommended in seismic zones. This kind of structures, even this kind of structures are not recommended everywhere. You can see when you are constructing this kind of slabs, which are called flat slabs, you may have higher span in between the two columns. Okay, we will understand what is this particular span. Generally, we consider 4 to 5 meters or maybe 3 to 4 meters. But in that case, you may have very higher spans in between two columns. But the thing is, this particular system is not recommended because we do not have a secondary media to transfer the load except this column and except this column, right? So if any of the parts, suppose this particular part is failing, in that case there will be nothing else to take the load of this particular flat slab, right? So that's why even if I talk about the lateral forces, we will explain it later why in case of seismic zones or lateral force where lateral force is higher, we do not recommend the code do not recommend this kind of structural systems. We will understand this. But the thing is, this is also a kind of RCC structural system where we may not have beams. So don't say that this is not correct. This is also correct, but it is a different kind of system, and the load transfer media is only from slab to column. Okay, and obviously the design criteria will be different than the regular RCC structure, right? Now here if you see that there is no extra part in this column, but here you can see there is a different extra drop. We call it as drop, like extra concrete it has provided to take the load of the slab coming to the column. These are called drops, okay, to restrict the punching shear. And there are a few more concepts regarding this. We will touch it later, but just understand this, that this is also a kind of RCC structural system that we can see in different areas, maybe in minor seismic zones. Okay, so let me go to the another system where, so previously what we have seen that we have beams, columns, slabs and foundation. Again, we have seen that we may not have beams, we may have only slabs and columns. Now here in this kind of structure, you see that along with the columns there is another system here. There is another system here. Even if you see this particular elements. So when we have horizontal forces higher in a structure, and when the structure is very tall in terms of height, so in that case the columns may not be capable of taking all the forces coming to the structure. Okay, we will discuss this in our next lecture when the evolution of structural systems. It will be our next lecture. So just understand that when we will be having higher tall buildings, even in nowadays in smaller buildings also, G+5, G+6 also, you may see this particular element. So we introduce this kind of element, which is called, it is a wall, right? It is a wall made up of RCC. Okay, a wall made up of RCC, and this particular wall is meant to take mostly the lateral loads, means horizontal forces. Horizontal forces. So this particular element is meant to take the horizontal forces mostly. Okay, we will discuss it later, as I have said. So this particular element we call it as shear wall. We call it as shear wall. So this is also a part of RCC structural system. Now shear walls can be made up of steel plates also in case of steel structures, but as we are talking about, as our course is about RCC building, so I'm explaining it in a building like structures. Okay, so you may see this kind of element. It is kind of column only. Suppose you have a column like this, and these kind of walls will be provided like this, where in one direction the length will be higher. Okay, the ratio of length to the width will be very less. Okay, so what is the ratio for that we will understand later. So in a RCC structural system, if you see, this is also a kind of you can say element, structural element that you may find in a RCC structure, right? So now if I go to the loads part, so if I talk about the gravity loads, that means the loads which are acting towards gravity. Okay, that means downwards in most of the cases. So there are two type of loads. One is dead load, another one is live load. Now what are dead loads? The name itself, it is a pretty easy to understand from the name, that dead loads are the loads which will be dead. Dead means it will be staying at this particular area forever, yeah, for most of the time. Like if you are constructing a wall, suppose this is the beam, this is the column, and you have constructed wall here. Here obviously there will be columns, and you have constructed walls here. So like brick walls here. So this brick wall is permanent unless or until you are going for any extension in the building. This brick wall is permanent. So the load coming from this brick wall to this beam, we can consider this as a dead load, because the load is dead here. That means it is constant here for most of the time, or maybe forever. Or if you have slab the floor and you have given the tiles, right, the floor finishes, this is also permanent thing. This is also permanent, right? So this kind of the loads coming from the tiles or floor finishes on the floor, we can call it as dead load. Or the load of these particular elements, this column, beam, slabs, they also have their own weight which is acting downwards, right? They also have their own weights which is acting downwards. You can see here these arrows. So their own weights, or you can call it as self weight of the elements. So the self weight of the elements are also, we can call it as dead load, because this load is constant here. It will not change if we talk about the gravity loads. Now suppose there will be obviously when you construct a building, people will be living on it, or if it is like a you can say commercial building, like a shopping mall, hundreds of people will be moving every day. But you cannot say that at this particular area all the time there will be one person. No, there cannot be. There might be 2 person, there can be 3 person, or there will be no person staying on this particular area, a particular area on the floor, right? So the load which is not constant, it is changing with time, or maybe it is changing now and then. So the gravity load which is not constant, we call it as live load. So with what load actually it is changing? Like the load of the human being who are moving around in the building, that is what we call it as live load. Okay, now this dead load, to find out the dead load, we have a code which is IS 875 part 1. Okay, in this code, what they have given the unit weights of the material that we'll be using. Suppose we have vitrified tiles or different kind of tiles. Okay, we have this RCC red brick walls, or maybe AAC blocks. So what is the unit weight of those elements, it is given in this IS 875. Now depending on the thickness of the wall, depending on the thickness of the you can say floor finish, you can find out the dead weight or dead load coming on the slab. Even it is given the unit weight of RCC also. Okay, and if you get the unit weight depending on the volume of this particular RCC element, you can find out the weight of this particular element, right? So to find out the dead load, we have this IS 875, which is giving us the unit weight of the you can say material. And for the live loads, it is not possible to provide any unit weight of a human being, right? Or if any the moving load on the building. So in that case, what they have done a kind of research, and they have came up with some particular values depending on the depending on the area of occupancy, like or the type of occupancy. Suppose you have a bedroom. So this is a very personal area. Maybe 2, 3, 4 members will be, hardly 4 members will be coming here. Okay, then we have drawing rooms. So in a building, in a residential building, most of the people will be gathering in this drawing room itself. Then we have kitchen. So depending on the occupancy of the rooms, or depending on the type of occupancy in the different areas in a particular building, what they have done, they have given some constant values of the loads. Obviously you can always change it with proper you can say proper logic, why you want to increase the load or decrease the load. But they have given some you can say experimental not experimental, they have given some values for our to make our job easy, so that we can easily put the values there. Otherwise you need to find out what is the load coming on, or how many people will be coming to your room, right? So the code which is giving us this kind of values, it is called IS 875 part 2. From this code we can easily get the load, and you can put on the structure. Okay, so this is about the dead load. Now if I go here, you can see in a structure, in a building structure, there can be loads from the horizontal direction also. There can be loads from the horizontal direction also. Now what are the loads that we may get from the horizontal direction? First, I should write this wind load at the first, because this is the load we see commonly every day. Okay, and in case of storms, the wind load used to be very higher. The pressure that the wind create in our structural members, like this, you can see, right? So if it is a structure, so we may see wind force like this every day. So this is the wind force. So this is one type of lateral, or you can say horizontal force on our structure. So suppose the horizontal force is coming from, let me just omit this. Suppose the horizontal force is coming from this side, as you see here. It is acting in this panel, this wall panel, and this force directly acting on this, like it is transferred to the columns and beams. Now the same force will be transferred, partial a part of the load will be transferred to the other elements also available in this particular structure, and the transfer of that load is done by the slabs of this available in the floor level. Okay, and as it is transferring the lateral force, that's why we call this particular element as diaphragm, or let me write it here properly. We call it as diaphragm. What it is doing actually? It is transferring the lateral force to the vertical members. It is transferring the lateral force. It is taking the lateral force from here, and it is transferring to the vertical members. Right? It is transferring to the members which will be actually resisting the lateral, the act of the lateral force. So we call this, the floor slabs, as our diaphragm. Okay. Now same as in case of seismic force. Now actually seismic force or seismic load it's not a direct force like our wind load, because the seismic activity, if you see, it is just a ground shaking. The ground is to shake, right? Now when we have to and fro motion in the ground, what actually we get? So in the case of the building design, we find out the base shear, or what is the base reaction that we are getting at this base level, and then we distribute this force like this. Suppose this is my building. We considering this particular area as fixed. Fixed means there is no movement in this node, this particular point. So obviously we'll be getting a reaction if we have forces from this direction, this movement. And after find out this force as VB, we call it as VB, we will explain it later. So this force, or you can say this base reaction, we distribute to all the floors available in this structure. Let me just increase some more floors. So we used to distribute it like this to all the floor levels. Okay, so this is suppose this VB will be distributed to F1, F2, F3, F4. So it is not a direct force like wind. It is a pseudo force, you can say. That actually the force, or actually it is acting at the ground level, and then we are distributing this after finding out this base reaction, we are distributing it as a load on the ground, you can say on every floor level. And as we are giving this load at every floor level, like suppose here, so from the floor level it must be transferred to the vertical elements, these vertical members, the columns. We know that this like the vertical members in a structure, in RCC structure we call it as columns, horizontal members we call it as beams, right? I must have said that in the first very first slide itself. So now this should be transferred to the vertical members, because these are the members which will be you can say acting to you can say to restrict the movement due to this particular forces. Okay, or you can say these are the members. Here you can see the shear wall also. If the force is coming from this direction, the force will be also this force will be also restricted by the shear wall itself. Restricted means the force will be transferred to the shear wall, and it will be taking care of the lateral. Okay, so this again, when we are talking about the seismic force or seismic load, this load also transferring the slab is transferring the load to the columns or to the vertical members, and this phenomena or this act of the slab to transfer the you can say the lateral loads to the vertical members, it is called the diaphragm action, and that's why we call this the RCC slab as our diaphragm, right? So we will discuss about this diaphragm and all in a later stage. So this is the fundamental discussion about the RCC structure, the general RCC structure. You can see whenever what kind of, doesn't matter if it is a you can say lateral or vertical load. If you have a vertical load, it will come to slab, from slab to beam, and from beam to column, as we have seen here. It will be coming to the slab first slab, from slab to beam, from beam to column. And in case of lateral members also, lateral forces also, here you can see it is acting at the floor level, from here to beams, beam to columns. The workflow is same even in case of lateral force also. Okay, so this is the basic understanding. Now there are different many loads, like we have temperature load. If I write fifth load, we have temperature load, which we may consider. We have blast load, which is very rare. In very rare kind of structures we'll be using it. We have blast load, or we may have different kind of, like the load of the machines. Okay, we have vibration. We also consider vibration in a floor. If you have a vibration, suppose you have a floor where you will be having the different machineries that create enormous vibration. So we need to consider the effect of vibration also in terms of a load. right? So there can be so many things, but in general these are the few things that we have. One is gravity load, another one is lateral load. And if you see the division, in gravity loads we have dead load and live load. Now we can differentiate the dead load and live load in different ways. And we have lateral load, seismic and wind. Okay, and we will see while we will be designing the structure in the seismic load also we may differentiate in different ways. Okay, but the thing is the load transfer mechanism is same from slab to beam, beam to column, or beam to shear wall, right? But in flat slab system we don't have the middle one, which is the beam. So the load is directly transferred to the columns. The load is directly transferred to the columns, right? So suppose you have a lateral force from this direction, and here this column failed, or these two columns failed. So what will happen? In between there is no beam to transfer the load to the other columns, right? Like there is no secondary media to transfer the load which this columns cannot take, couldn't take, right? So you will see that the you can say the tendency of failure in this kind of structures are more than the structures with beams and columns. And the structures with beams and columns, if you see, if you have a structure like this, suppose these are the beams and these are the columns, and the connection between these beams and columns, these are actually rigid connections. So if the horizontal and vertical members are connected with rigid connections and creating this kind of you can say frame, we call this kind of structures as frame structure. Okay, or we call this as a frame. Horizontal member and vertical member connected to rigid connection, and this creates a frame actually. Okay, and including different kind of frames, including different shapes of frames, if we create, combining all these frames, if we create a structure like this is a frame structure. Okay, so the type of structures, the evolution of structural system we will discuss in our later session, but this is what the fundamental you can say load transfer mechanism is, and this is what we should understand first. Okay, so this is the first session. I think that's it for the first session. So this is not for everyone, like those who are just starting their you can say their understanding in structural engineering, or their understanding in civil engineering, the third year students, second year students. Obviously it is not for second year students, for third year onwards. So those who are getting the concepts of RCC and the loads and all, so for them I have just created this this basic you can say lecture. Obviously it is not for all, because those who are practicing engineers, we all know these things very well, even in more depth than I have explained today in this lesson. So there is no need of, you can say no need, I won't say no need, but you may get bored with this particular lecture, right? So I will not say that you should watch this, but those who are starting from the very scratch, this is for you. And in our next lecture we will see about the evolution of structural systems, how the structural systems have changed over the years depending on the need, depending on the different conditions of the load, okay, depending on the height of the building. So this we will see. So that's it for this lecture. We will see you in the next lecture. Thank you.